This is the first experiment in acid-base titration. The basic purpose of acid-base titration is to determine the concentration of an acid or a base whose concentration is unknown by using another solution whose concentration is already known. For this experiment, we need a pipette, pipette filler, funnel, iron stand, burette, beakers, and a conical flask. The chemicals required are a 1 molar sodium hydroxide solution, an HCl solution of unknown concentration, phenolphthalein indicator, and distilled water. First, wear gloves for safety because these chemicals are quite strong. This is a 1 molar sodium hydroxide solution, and hydrochloric acid is a highly corrosive acid. That's why I'm wearing gloves for protection. The first step is to fill the burette with the sodium hydroxide solution, whose concentration is already known, using a funnel. Insert the funnel into the burette and make sure the stopcock at the bottom is tightly closed. Once it's securely closed, pour the sodium hydroxide solution into the burette through the funnel. Then carefully place the funnel aside. You'll notice that I've filled the solution slightly above the 0 mark. I'll explain why. When filling a burette, air bubbles can sometimes become trapped inside. To release them, gently tap the burette. If there are any bubbles, they'll come out. In our case, everything looks fine. I can't see any air bubbles. Now we'll slowly release a little solution until the liquid level reaches exactly the 0 mark. Notice that the surface of the liquid is curved. This curved surface, called the meniscus, is formed because of the surface tension of water. Since there are no air bubbles inside the burette, we can now adjust the meniscus to the 0 level. Always take the burette reading by looking at the center of the meniscus, not from the sides. The liquid appears slightly higher along the edges because of its curved shape, so the correct reading is taken from the lowest point of the meniscus. I think it's now exactly at the 0 mark. Now wipe the tip of the burette with a tissue so that no hanging drop falls into the flask later and affects our measurements. With that done, let's move on to the next part of the experiment. Now we need our hydrochloric acid solution. For that, we'll use a pipette. Attach the pipette to the pipette filler and first remove the air by pressing the air valve. This creates a vacuum inside the filler. Next, press the suction valve so the acid starts entering the pipette. This is our bottle of hydrochloric acid, whose chemical formula is HCl. We'll transfer exactly 10 milliliters of HCl into the conical flask. We begin at the 10 milliliter mark and carefully allow the liquid to flow until it reaches the 20 milliliter mark. As you can see, we've gone from 10 to 20, which means exactly 10 milliliters of acid has been transferred. Any remaining acid in the pipette is returned to the original bottle. The next step is to add phenolphthalein indicator. Phenolphthalein is pink in a basic solution, but remains colorless in an acidic solution. Right now, our flask contains only acid. As we gradually add sodium hydroxide, it will neutralize the acid. The moment the acid is completely neutralized, even one extra drop of sodium hydroxide will make the indicator turn a permanent light pink. That pink color tells us that the reaction has reached its endpoint. We'll then record the volume of sodium hydroxide used from the burette. Using that known volume of sodium hydroxide and the known volume of hydrochloric acid, we'll calculate the molarity or concentration of the hydrochloric acid solution. Only 1 to 3 drops of phenolphthalein indicator are enough. This indicator is light sensitive, which is why it's stored in a dark glass bottle. The bottle protects it from ultraviolet light, preventing its molecules from breaking down and keeping the indicator effective. Now let's begin the titration. Don't open the burette valve too quickly. Allow the sodium hydroxide to flow slowly into the flask. First, gently swirl the flask to mix the indicator evenly. Since the background beneath the flask is white, it will be easier to notice the moment the solution starts turning pink. Keep swirling the flask continuously while adding the sodium hydroxide. Since I'm right-handed, I'll swirl the flask with my right hand and control the burette valve with my left hand. The reaction can be quite vigorous because both sodium hydroxide and hydrochloric acid are strong chemicals. Therefore, we'll add the sodium hydroxide very slowly, drop by drop. Hydrochloric acid is commonly known as muriatic acid, while sodium hydroxide is commonly called caustic soda. When they react, they form sodium chloride and water. In this reaction, 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide. Therefore, the stoichiometric coefficients are N1 equals 1 and N2 equals 1. Let's increase the flow rate a little. Keep swirling the flask continuously so that as soon as we notice the first faint pink shade, we'll immediately reduce the flow rate and start adding the sodium hydroxide more carefully. I think the hydrochloric acid concentration is fairly high, so I've increased the flow a bit to reach the neutralization point more quickly. Students, keep noting the burette readings as we proceed. From these readings, we'll determine the volume of sodium hydroxide required to completely neutralize the hydrochloric acid. So, we already know that N1 equals 1 and N2 equals 1. We also know the volume of hydrochloric acid, which is 10 milliliters, but we don't know its concentration. We do know the concentration of the sodium hydroxide solution, which is 1 molar, and now we're going to determine the volume required for neutralization. Nothing has happened yet, so I think I'll slow the flow down a little. This acid seems to be very concentrated. Almost 20 milliliters of sodium hydroxide has already entered the flask, but there is still no permanent color change. I think we're getting close to the neutralization point. As a few drops fall into the flask, you can see a faint pink color appearing for a moment. There it is again, a very light pink shade. The color appears briefly but immediately disappears because there is still excess acid present. I think we'll probably see the permanent color change after the 30 milliliter mark. You can already notice a very faint pink tint beginning to appear, but it keeps fading because the acid is still neutralizing the sodium hydroxide. The moment this pink color stops disappearing and remains in the solution, that will be our endpoint or neutralization point. We've now crossed 30 milliliters. This acid is extremely concentrated. How do I know? Because it's taking roughly 3 times the volume of sodium hydroxide to neutralize it. We started with only 10 milliliters of hydrochloric acid, yet we've already used more than 30 milliliters of sodium hydroxide. The flask has become quite warm, and the acid still hasn't been completely neutralized. Every bit of sodium hydroxide we're adding is still reacting with the acid, so we may need even more sodium hydroxide. Students, our entire burette is now empty, and the acid is still not fully neutralized. This is a very highly concentrated acid solution. So, what do we do now? We'll simply repeat the same procedure. We'll place the funnel back into the burette and refill it with sodium hydroxide solution. Tighten the stopcock securely, adjust the liquid level back to the 0 mark, and allow the excess solution to drain until the meniscus is exactly at 0. Once again, make sure there are no air bubbles inside the burette. You can see a few small bubbles forming here, and now they've disappeared. We'll set the level back to 0, place the flask underneath, and continue the titration exactly as before. We've already used 50 milliliters of sodium hydroxide. Let's see how much more is required. Oh no! Now we need to slow down because the pink color is beginning to stay visible for a little longer. That means we're getting very close to the end point. I'll speed it up just a little again. Keep watching both the color change and the burette reading carefully. The acid is still present, so we'll add a little more sodium hydroxide. I think I made a small mistake. Right at the end, I released the sodium hydroxide a little too quickly, and we've gone slightly past the end point. The pink color is no longer fading, which means we've crossed the neutralization point. Let's record the reading. It looks like about 11 milliliters more sodium hydroxide was added after refilling the burette. Since I accidentally added a little too much at the end, this is something you should avoid during your own experiment. Always add the solution drop by drop as you approach the end point. I'll close the stopcock now. The reading is just slightly below 11 milliliters, but to keep our calculations simple and account for the extra solution added accidentally, we'll consider it as 10 milliliters. Since we had already used 50 milliliters, adding another 10 milliliters gives a total of 60 milliliters of sodium hydroxide required to neutralize the acid. As you can see, the solution now remains permanently light pink, which means the hydrochloric acid has been completely neutralized. At the beginning, we only took 10 milliliters of acid, but because its concentration was very high, it required a much larger volume of sodium hydroxide to neutralize it. And that's our titration complete. Now let's perform the calculations, and afterward we'll pour the remaining sodium hydroxide back into its storage bottle. So students, let's move on to the calculations. Our balanced chemical equation is HCl plus NaOH yields NaCl plus H2O. From the balanced equation, we can see that 1 mole of hydrochloric acid reacts with 1 mole of sodium hydroxide, so N1 equals 1 N2 equals 1. The volume of hydrochloric acid was V1 equals 10 milliliters. Its concentration, M1, is unknown. The volume of sodium hydroxide used for complete neutralization was V2 equals 60 milliliters. The concentration of sodium hydroxide is known. M2 equals 1 molar. Now we'll use the titration equation. M₁V₁ over N1 equals M₂V₂ over N2. Substituting the values, M1 times 10 over 1 equals 1 times 60 over 1. Since both denominators are 1, M1 equals 60. Therefore, M1 equals 60 divided by 10 equals 6 molar. So the concentration of our hydrochloric acid solution is 6 molar. It is 6 times more concentrated than our 1 molar sodium hydroxide solution. This is a very strong acid, so always handle such concentrated acids with great care and respect. That's the end of today's experiment. Let me know in the comments how you liked this experiment. If you have any questions, feel free to ask them in the comments below. Thank you.